Hey, welcome back. In the last video, we introduced organometallic reagents. Really, we introduced a review of organometallic reagents. And in this one, we're going to follow it up with the reactions that we can see with them. So we talked about organolithium, which is an R group or an alkyl group, some carbon chains, however you want to think about this R group, bound to a lithium. We talked about a Grignard reagent, which is that R group bound to MgBr. And we also talked about organocuprates, which is that R group bound to a CuLi. And in all of these, what you're forming is a nucleophilic R group. So an R group with extra electrons, it's got a negative charge, it's nucleophilic, or it craves the nucleus, that positively charged nucleus of an atom. And so first up, we're going to see what they do in aldehydes or ketones. Actually, first let me make it a distinction. Organolithiums and Grignard reagents are stronger organometallic reagents than the organocuprates. I talked about that a little bit in the kind of mechanisms of the last video, but I just want to reiterate that the organolithiums and the Grignard reagents react in a really similar way, and they're both pretty aggressive. So with aldehydes or ketones, you're going to see this R group add to the carbonyl carbon, and it's going to look like this. You've got either that aldehyde hydrogen or the ketone R group. You've just added on this R prime from the organometallic. You've got this negatively charged oxygen now because the electrons get pushed up to the oxygen, and it eventually gets protonated. So I'll draw it like this. It eventually gets protonated. And so you're going to end up with an alcohol. With esters, again, you're going to need a pretty aggressive organometallic. A cuprate is not going to be a good idea for this reaction, but again, that R group is going to attack the carbonyl carbon. Remember that carbonyl carbon is partially positively charged. The electrons again kick up. In this case, though, because the oxygen, the methoxy right here, methoxy, if this R is one carbon, but this OR right here is a good leaving group right there. So it's going to hightail it out of there and taking its electrons with it, allowing the, let me draw that intermediate right here. So those electrons had moved up here to this oxygen, so it has 3 lone pairs of electrons up on it now because the R group has moved in. But that OR group left, taking its electrons with it, allowing these electrons to come back down. And so the carbonyl double bond reforms, and it allows you to add another, let me get another color here. It allows you to add another nucleophile, another carbon nucleophile to that carbonyl carbon, and it goes all the way down to, whoops, yeah, I want to keep the green. So now you've got 2 of these, 2 of the R primes that came off the organometallic, either the Grignard R's or the organolithium R's. And now you've got, again, that negatively charged oxygen because the electrons have kicked back up. And you follow that with an aqueous workup where the oxygen can abstract a proton. So that's with esters. And remember, this needs to be at least 2 equivalents of the organometallic there, or you might see it written in excess. And stick with organolithiums or Grignard reagents. With acyl chlorides, the chloride is a pretty decent leaving group there, and so the organolithiums and the Grignard reagents are going to do the same thing that they did when the OR group left, and they're going to react twice, adding on 2 of their R prime groups, and then eventually allowing that oxygen to be protonated in the aqueous workup. The organocuprate, or the Gilman reagent we called it, it isn't as aggressive, and so it's only going to react once. You know, the chloride is a pretty good leaving group, and so it will add on to form, you know, eventually initially, let me erase this and show you the 2 steps for it. Initially, it'll react a lot like the other organometallics did, and it'll kick those extra electrons up to the oxygen as it adds that R group. The Cl will have left, taking its electrons with them. It'll allow the electrons from the oxygen to kick back down and reform that carbonyl double bond, that carbonyl double bond. Except with the organocuprates, it's not going to react again. The organocuprate isn't really aggressive enough to react with an aldehyde or a ketone, so it's going to stop right there, whereas the stronger organometallics, the organolithium and the Grignard, will take it all the way down to an alcohol, adding 2 of their R groups on. With epoxides, any organometallic, so I just wrote Rm, that can be the organolithium, it can be the organocuprate, it can be the Grignard. They will all react with these epoxides. To open up the epoxide, you're going to see the R group come in. I intentionally made these hydrogens and these methyls right here because the R group, that nucleophilic R group, is going to come in to the least substituted side right here. In this case, the hydrogens, it's going to do a backside attack, and it's going to force it'll look like this, the hydrogens. Where the R is over there, and it'll force that oxygen up and over here, and that'll initially have a negative charge as it gets pushed off. Like so. Now I realize that stereochemistry isn't a big deal because these are both methyls here, and this really isn't a chiral center. But if they were different, this is the stereochemistry it would have, and then this gets protonated with the aqueous workup, such that the R group that was added, that nucleophilic R group that just got added, and the alcohol group here are on different sides. So they're always going to be trans to each other, and you're going to get a 50-50 mix of the enantiomers here. You know, this R group might be in the back, or it might be in the front over here, but keep in mind that the alcohol group, this OH over here, is going to be on the opposite side, trans to the nucleophilic R group. Moving along, I have another video up that's a little more exhaustive on alpha beta unsaturated carbonyls, but just a refresher, these are groups that have a carbonyl group right here with the carbon oxygen double bond, and then one sigma bond away, this is a sigma bond, so one sigma bond away you have a carbon-carbon double bond. And it creates a pretty neat scenario where you've got a partially positive charge on the carbonyl group, and then through resonance, another partially positive charge on what we call the beta carbon. Remember that the carbon from the carbon-carbon double bond that is closest to the carbonyl carbon, which is that one, is the alpha. So I know I'm drawing a lot of stuff on here, kind of making it murky, but this is the alpha carbon, this is the beta carbon, the carbonyl carbon, and the beta carbon are the ones with the partially positive charges. And so it creates two different ways that that this reaction can occur. It can occur 1-2, where the carbonyl group is attacked, and then the oxygen from the carbonyl group is protonated. And so that happens with the stronger, more aggressive organometallics like organolithium and Grignard, and it ends up looking like this, where the R group adds on to the carbonyl carbon, like right there, and then you have a negative charge as those electrons get kicked up to the oxygen that is eventually protonated with the aqueous workup, such that your product is the protonated oxygen and the R1 group added to the carbonyl carbon. Or with organocuprates, because of several reasons, including molecular orbital theory and just the kind of the electrostatics of the reaction, the R group from the organocuprate is going to attack the partially positive charge on the beta carbon right there. And so it creates the possibility of the negative charge, these electrons being kicked to the alpha carbon, or through resonance going all the way up to the oxygen. And so and this is, keep in mind, this is called the 1,4 or the conjugated addition. And you have two options here. The R group is added to the beta carbon, and you've got the negative charge on the alpha carbon, and it gets protonated there. So that's one option. Or you've got the R group, that nucleophilic R group, being added to the beta carbon, and then these negative these electrons that were kicked to the alpha carbon coming down and forming a bond here, kicking the electrons from the carbonyl group up to the oxygen, and then allowing it to be protonated. And so that's the other option with the 1,4 addition. But I'll tell you that this right here, if you have to do a 1,4 addition, the one with the carbonyl group still intact is going to be the favored one, because in this keto-enol tautomerization right here, which I did some notes on before, the keto form of the keto-enol tautomer is the more stable form. So really, if you want to simplify it, you can think of the R group just adding to the beta carbon, and then immediately that alpha carbon right here getting protonated. So one last one. This is running a little bit long, but we're going to talk about acid bases. And the big thing to remember is that anytime you have an organometallic reagent, you're forming a pretty strong base on your R group. And so as a strong base, it's a heavy electron donor, and it'll rip a hydrogen off of a pretty weak acid. It doesn't take a very acidic hydrogen for this really strong nucleophilic base of an R group to pull it off. And so if you have an OH group present on an OH or an NH, OH or NH present on the compound that you're using this reagent on, it's going to not add to the partially positive charge. It's not going to add like a nucleophile normally would, and instead it's just going to do an acid-base reaction. And so you'll see the R group come away with the H, and then you will have the positive aspect of the the metallic, whether it was the lithium or the MgBr or the CuLi, and then you'll have the conjugate base right here, or in the case of a carboxylic acid, this would be your conjugate base. And these are called oxalate ions right here. So anyway, the way you stop that from happening is by adding a protecting group on there. And the protecting group, it's a pretty magical little reaction where you add a group on here, it substitutes the H for something else so that the organometallic can't react with it, can't do an acid-base reaction, and will actually react on the carbonyl carbon or whatever partially positive carbon that you want the organometallic to react with. And then at the end, you can just take that protecting group off. So the protecting group is going to be ClTbDms. That's the protecting group. And then it's going to come off looking like this, where you have actually no, it's going to come off looking like this, where you have the TbDms on there. And TbDms stands for tert-butyl dimethylsilyl ether, or in this, like at this point, it's just silyl. But it does this number where you have the O bound to the tert-butyl DMS, and that protects it so that when you do your reaction, and say, let's just say we're going to add an ethyl group on there with a Grignard reagent, so EtMgBr. You added this on, you've still got the OTBDMS, and then you can just take the protecting group off, and all you do is put it in tert-butyl ammonium fluoride, or TBAF, and that just takes your protecting group off and replaces the hydrogen where it was, so it comes out looking like, sorry, that would get protonated, my bad. So it comes out looking like this. Anyway, pretty cool. A way that you can keep the organometallics from doing an acid-base reaction, because again, the acid-base reaction is so much more favorable than the nucleophilic addition. So if you have a hydrogen that's very acidic at all, so on an alcohol or on an NH group, carboxylic acids have that. There are several others. You have to protect that OH group with a protecting agent, and you do that through TbDms, which is tert-butyl dimethylsilyl ether, and then you take that, you do your reaction, and you take it right back off with TBAF. So I hope that was just like a pretty quick run through of the reactions you can do with organometallic reagents. See you later.